will be on the strain gauge. Okay, so strain gauge measurements, strain gauge transducers first, and then in the following classes we will see the basic in the measuring chain of some transducers. So the first question that I have for you is, what are strain gauge meant for? Yeah, right, correct. Measuring strain is their purpose. Okay. Now, do you have an idea of what is the reference numbers? So what we are expecting in terms of strain, the measurements of such a strain. I mean, what is the typical value of the strain measurement? What is the unit of measure of strain? You have an idea?
Meter?
Yeah, meter.
Meter? Kilonewton, not at all. Do you remember what is the definition of strain?
Strain is the change in the displacement, the ratio of the changing displacement into the first length. And I think it is dimensionless.
Yes, you're right. You successfully passed the aerospace structure exam, I see. So, for sure, the strain is dimensionless because it's the ratio between the change of the length with respect to the reference length. Or, in other words, it is the unit change of length. Okay, so generally speaking, the strain.
Are you recording this?
Oh, sorry, I have to. Thank you. How can I do that? Yeah, like this. Yes. Okay, I'm going to record now. Thank you for reminding me. I always forget this. Should start somewhere. Yeah. Okay, so the strain is in one direction. So there is a tensorial definition of strain, but however, its meaning is that there is a unit change with respect to the reference chain. Okay, so the change of the length with respect to the reference length. Now, so is dimensionless. What are the typical values? I mean, values of the strain that are generally found in the aerospace engineering. I mean, we can have a variety of values, of course, but when we are designing, when we are testing structures, what is the general value according to your experience? Just to have an idea about that, let's consider, just to have fun at the beginning of the class, the child's toy, the seesaw, teeter-tooter, swinger. I mean, something to play with, especially designed for children. So it is something, let's say, of this kind. Okay, there is a road, for example. Then we are hanging on a weight. Okay, like this. This is the weight. So let's assume, for brevity, that we have this structure. Okay, that is made of a solid tube, for example. Diameter is 1 centimeter. And let's say I am hanging on this toy, okay, so that, for example, the weight is about, let's say, 80 kilograms times G, so about 800 newtons. More or less, doesn't matter. Then what? Can you estimate the value of the strain, axial strain for this solid road when subjected to my load? I'm not entering into many details of the swinging, just hanging over there like that. In order to do that, remember, we have first to find out the stress corresponding to this external loading. It is a 1D stress because of the structure. So the corresponding stress is given you by the ratio between the actual force and the actual section, okay, cross section. The actual force is my weight, and the actual section is something that reminds me pi phi square 4. Okay, so if you made the numbers, so what you can have is that the stress is of about, let's say, 10 megapascal. You can check by yourself the result. Now let's assume that we have an aluminum rod, solid rod. What we got is that the corresponding strain, is given you by the ratio of the stress corresponding to the Young modulus, okay, E. That is more or less of about 145 microstrain. If you have a steel rod, then steel rod means to me 300 gigapa in terms of a Young modulus. Here, E is equal to 70 gigapa, okay, as Young modulus. So what we got, again, once again, sigma over epsilon is about, let's say, 35 microstrain. Microstrain, remember, always remember, is 10 to minus 6, okay, meters over meter. So these are typical values, okay, of strain that have to be measured, that has to be tested. That's not just for fun, just having measurements. So the reference, the typical quantities that have to be measured is about 100 of microstrain. If you're having thousands of microstrains, then we are going to have a very large strain, okay? So we are almost at the limit of linear elasticity model, okay? Generally, we have about 10 up to 100,000. It's okay, but we are at the border. We are okay of the linear elastic models, generally speaking. So, what is the idea behind here, the strain gauge measurement? The idea behind the strain gauge measurement is, once again, to have a transducer that is capable to transduce your physical quantity, the strain, into an electrical quantity. There are many working principles that are used to measure the strain. The one that we are going to see is what is generally referred to as a resistive based strain gauges. Why resistive? Because what we are having is that the working principle is based on a change of the resistance, because the resistance is bonded to the structure somewhere in a specific location, and the structure is reacting to external force through a strain. Okay, so you remember when you were very, very young, and at those time teachers taught you how to identify the electrical resistance from the geometrical and material property of the electrical wire. This is the one of the Ohm's law. Okay, the resistance, the electrical resistance, is given you by this known formula. You remember that? In which L is the length of the wire, A is the cross section of the wire. Rho is called the resistivity of the wire. Okay. Now, the idea is that what we would like to have is that now we bond this wire, characterized by a reference resistance, electrical resistance, to the structure. Then we apply an external load to the structure. Because the resistor, the electrical resistance, is fully bonded to the structure, what is doing the structure is what will be doing the resistance, so that if the structure is changing the shape, is having a strain, then the electrical wire is changing its shape. Okay, the idea is that try to link this change of resistance because the wire is changing to the corresponding strain. Now, as we can see here, we are considering a resistor that is having a finite change, okay? Now, let's assume that because of the change, there is general change of the physical parameter. Oops. Physical parameters, whatever. So the change of resistance is, of course, a function of the change of the resistivity, the change of the length, and the change of the cross-section. Okay. Now, let's assume that because of the physical quantity that we want to measure, that is, because the strain is generally very, very small, microstrain is my reference value, we can assume that from finite differences, finite changes, we are moving to very small infinitesimal. Okay, so from finite to infinitesimal changes. Okay, because everything is small, what we can say is that the change of the resistance could be thought as a superimposition of the three different effects that we are having by changing time by time. First, the resistivity, then the length, then the cross-section. Okay, everything is small. What we can say is that the overall change of resistance is given us by the sum of all the three independent changes of resistance. Okay, that is, we can write that the variation, sorry, the change of the resistance could be seen as the change of the resistivity because the resistance because of the change of resistivity, while keeping the other parameter constants, that is the length and the cross-section constant, okay, times the variation of the resistivity itself. Then the other contribution is the change of resistivity because we are changing the length while keeping the resistivity and the cross-section constant. Finally, times the change of the length. The last contribution is the change of the resistance because we are changing the length by keeping the resistivity and the length constant, time the change of the cross-section. Okay. Now, in those conditions, and by recalling that the resistance here is a function, is a well-known function, the resistivity, the cross-section, and the length of the wire, the first equation that I wrote then we can substitute, or we can take the derivatives of the resistance just by taking the equation that I'm showing you on the screen right now. And then what we are having is that the change of resistance with respect to the resistance is given by the variation of the resistivity with respect to the resistivity plus the change of the length with respect to the length negative the change of the area with respect to the area. Okay. Please know the change of sign, because when taking the derivative with respect to the a, we have a at the denominator, so it provides the negative sign. Partial derivative. Then we have just the same. Okay, we can keep the total derivative. Okay, because we had defined that these are the variation. Now, let's assume to consider one typical wire like this. No, change color. Okay, the wire is characterized by a cross section, circular cross section, radius r. Okay, and then it has an infinite direction in that way. The area, the cross section area, as you know, is pi r square. And so when computing the derivative of the a with respect to a, that is equal to the derivative of pi r square with respect to r, okay, divided by pi r square, and that is equal to 2 pi r divided by pi r square dr. Okay, thus the fractional change of the cross-section area is given you by 2 dr over r, but if you remember the meaning of the Poisson ratio, that is a cross-section reduction of the section, because we are having a length variation. So this dr over r is equal to negative Poisson ratio nu L over L. Okay, and this nu is the Poisson ratio. Okay, the Poisson ratio, remember, is telling you what is the relation between the change of length in one direction and the corresponding change of length in the orthogonal direction. Okay, so at the very end, what we got here is that the change of the area with respect to the area is given you by negative 2 nu and then L over L. Having said that, go back to your definition, or better, back to the variation of the resistance. What we are having is that the dr over r is equal to the change of the resistivity plus 1 to nu L over L. Okay. Now, what's the meaning of this last ratio, the L over L? The L over L, if you go back to the very beginning, yes, here, the L over L is your strain, okay, strain in the, let's say, longitudinal direction of the electrical wire, okay? So the principal direction. So we can refer to this L over L as your strain in the longitudinal direction. Let me call it that as the natural strain gauge direction. And that's what we got, is that the change of resistance in percentage, dr over r, is equal to the change of resistivity plus the strain 1 plus 2. Okay, and that is one important equation that we have to consider. Now, from the, let's say, theoretical point of view, this equation is very interesting. Why that? Because we can link the change of resistance in a wire perfectly bonded in a structure to the strain that this structure is having, okay, and to the change of resistivity because of the change of the shape of this wire, okay? Always thanks to the fact that we are exciting the structure with external load and the structure is reacting with a strain, okay? So from the measurement point of view, this equation is very nice, but it's not that nice. Why? Because we don't have a clear relation between the input, the strain quantity that we want to measure, and the output, something electrical that we are going to measure, so dr over r. In order to do that, let me introduce the gauge factor so that the r over r is equal to k epsilon, okay? In which k is your strain gauge factor, going to refresh factor, and this strain gauge factor is equal to 1 plus 2 ni, and then plus 1 over epsilon 0 over all. Okay, and this equation, this relation, is much more interesting from the measurement point of view, because we have something that is straight linking the input, the strain, and the corresponding output, the change of a resistance per unit of resistance. Okay. Now the problem is here in K, the strain gauge factor. Can you see the problem? You have an idea why I'm not so happy about this final resistance? There's the final equation.
Because we have differential in rho.
Say again, please.
Because we have differential in rho.
Different, I can see that.
I mean, because we have d rho over rho, we have differential.
Yeah. Differential. Okay, I see. Yes, mainly because of that. As you can see, there is K, the strain gauge factor is not a constant value. Okay, it is something non-linearly dependent on the strain itself. So that is very, very bad from the measurement point of view, because you have to know the unknown strain in order to have the K, the strain gauge factor, and thus you have the estimate of the strain. So it is very, very bad as equation to be used in real life. Okay, but let's assume for a while that the change of resistivity is practically zero. So if this is true, then what we got is that the K is 1 plus 2, 2 ni. Okay, and that is very nice because its value is approximately so that the strain gauge factor is between 1.5 and then let's say 2, according to the different value of the knee constant. Okay, so if you assume, for example, knee equal to 0.3, then you got 1.6, for example. Okay, and that is constant. That is very nice. However, in real life, this change of resistivity is not constant at all. So we have to consider this contribution, 1 over epsilon. We are lucky because this term is practically constant in the measuring range up to about 1000 microstrain. 1, 2 doesn't matter, that is equal. So that means that the change of the resistivity is compensating the actual strain, so that the resulting term is practically constant in our measuring range. Okay, and the result is that K is having a constant value of about 2, more or less, depend on the let's say on the measuring on the strain gauge itself characteristics. Okay. Yes, depends on something, on materials, but generally speaking, this K, the strain gauge factor, is constant and about 2. Okay, not large differences with respect to. Okay, there are differences if you go into details, you will see something in the laboratory, but 2 is the reference value for the K constant. So please open your DNA code and insert this new information. Okay, when you are dealing with strain gauge measurements, you have to deal with the strain gauge factor. We saw together how this strain gauge factor comes up. We saw together that this strain gauge factor is in principle a nonlinear factor of the strain measurement. But if you fail to remember that, however, these two contributions, the change of the resistivity and the strain, compensate each other, so that K, the strain gauge factor, is, however, constant, you won't pass your exam, final exam. Okay, so open the DNA code, put that information in, and lock your DNA code, so that you always remember that in strain gauge measurement, up to, let's say, 1000, 3,000, 4,000 microstrain, the K value is practically constant. Okay, thanks to the compensation of the change of resistivity with respect to the strain, measurement strain. Okay, and depends, of course, on the Poisson ratio, on the new value. Doubts on that? Now, the question is, how can we identify this K parameter?
Can you
the
actually
strain
repeat
gauge
that?
function? Say again, please.
Can you actually repeat that? It was breaking up a little bit.
What do you want me to repeat? The DNA code?
Yes.
So, if you go back to the main equation, that one in the block there, you can see that there is a very nice relation between the change of resistance and the strain. However, the strain gauge factor is not constant, is a nonlinear function of the strain. Okay. However, this is true in principle, but we can see in the typical measuring range of about 1000 microstrain, the change of resistivity compensates the actual strain, so that the strain gauge factor is a constant one, and its value is about 2. Okay, so despite the equation, that will lead us to say that there is a nonlinear relation. Actually, it is not. K is constant, and the typical value is 2. If you fail to remember this during your final exam, you won't pass the exam. Okay, that is of major importance. Okay, now if you would like to set up your own company producing strain gauge transducers, the problem is to give customers the information of the K plus other information. But now let's focus on this. So K is a strain gauge factor. How can I identify the K factor from the measurement? Because of course I can't say what is the ratio between 1 over epsilon and 0 over rho. Okay, so we have to estimate from the experimental activity the value of K. There are many approaches. I would like just to show you one among them. First, so experimental of the strain gauge factor. So first hypothesis is that there is no transverse sensitivity. Okay, so only the longitudinal behavior is of interest to me. That is, if you want the ratio of the cross-section dimension, the radius, for example, with respect to the length of the wire is very, very, very small. Okay, so that we can neglect all the transverse behavior from the reflection point of view. Then the second hypothesis, what we have is that bonding thickness negligible. Okay, so that the strain gauge is at the top surface of the structure. Okay, without any other interaction between the bonding device and the structure itself. So no glue effect, no anything, everything is there. Under this hypothesis, let's consider this very nice test setup. We have a beam. I know you are familiar with beams, okay? In these beams, there is an external loading, force F and F over here, so that both action line are apart from the constraint setup of a quantity equal to A. The beam is a rectangular, having a rectangular shape like this. Sorry, change color. Homogeneous material, thickness and width B, so that the neutral axis is at the midsection. Okay. Under these circumstances of the boundary conditions and material and shape, what I can say is that there is a uniform distribution of the bending moment. Okay, so the bending moment is constant through the beam and equal to F times A. Okay. Now I'm asking you, what is the value of the stress? And then what is the maximum value of the stress in such a condition? If you remember the Euler-Bernoulli beam model, what we can say is that the stress is equal to the ratio of the bending moment by the moment of inertia, okay? And then the distance, let's call it C, and then the distance C from the neutral axis. That is that your maximum value of the stress because of that bending condition is giving you the bending moment divided by inertia and then half of the thickness. Okay, no glue effect, no bonding device is considered. Very negligible. Once we have it, just consider the values. Remember the moment of inertia I is bt cube 12. Okay, so what we can say is that the maximum stress is the bending moment, is the bending moment that is F times A divided the moment of inertia, the Q12 times the thickness. It comes out that your maximum stress is 6F times A over the T square. How about the strain now? Once we got the stress, and once we are assuming that is a 1D strain distribution, this strain is just that one divided by the Young modulus. So it is equal to 6Fe over Young modulus, then Pt square. And that is the very nice relation that is currently used to estimate the strain that is undergoing such a kind of structure when loaded with a bending moment in a way that I just drew before. Okay. How about the strain gauges now? How about the K factor? Remember, we have just found out that the change of resistance with respect to the reference resistor is given you by K epsilon. So what we get is that the K strain gauge factor is given by dr over R with respect to epsilon. And this ratio dr over R is measured by a very precise measuring circuit that is called ohmmeter. That is very precise. Whereas this one, the strain, is estimated using the previous formula. Okay, so if you want to set up your own strain gauge company, trying to sell your strain gauge to all over the world, then you have to introduce specific tests so that you can provide your strain gauge with the corresponding strain gauge factor. You'll find out that by changing the loading here, F, okay, you will have different value of the strain, but you will have also corresponding different value of the change of the resistance, so that the K value is a constant one, okay, up to, let's say, some thousand microstrain, so 3,000-4,000, no more than that. Okay. Doubts about that? Okay. 3p, so give you 10 minutes break, okay, so that we can keep going with the class, let's say 3:10. Okay. Questions? Okay, see you back in 10 minutes. Yes? Yes, we will see at the end of the class now.